Today we're going to be talking about measurement error models and causal inference. And we're just going to scratch the surface, really. I just want to present these ideas and kind of let you know that this is a thing, and that if you're interested in applying it, obviously you're going to have to get more information. And so I just kind of want to talk about the basics of it and show you that it's there, that this research is there, and something you can apply if you have the data and interest to look at it. So we did the spatial methods. That was dish 3 actually, and today we're going to do the other two. There's less slides on these. And we're just going to answer some basic questions for each one of these. So we'll talk about causal inference and marginal structural models. And has anybody in here taken the causal inference class from FAN? Okay. It might be, I'm not sure, it might be kind of more of a PhD course, and it may not be offered every year. And so she I'm sure goes into much more depth on causal inference methods. And what we talk about today is just one modeling approach to try to get at causal effects, right? So to introduce this, you guys probably have talked a lot in previous classes about, correlation and causation, and that correlation doesn't imply causation. Just because you have two variables that are correlated with each other doesn't mean that one causes the other to happen, right? There could be other variables, mediators in particular, that could explain that correlation and that relationship. But to go even a step further, how do we typically try to estimate causal effects? In thinking about this, let's consider like regression modeling. How would you, let's say you have a predictor and you have an outcome. What would be the approach that you would typically try to take in order to get your best estimate of the effect for a predictor on an outcome? So again, think about what you do in regression.
I think you would try to adjust for potential confounders, and you would maybe think about interaction.
Yeah, that's right, Chloe. So you basically, we would add in other variables into the model. That could be confounders. That could be variables that are related both to the predictor of interest and the outcome, right? So we want to add more variables and get an adjusted effect. That's what we typically do, right? If we want to get a better idea of the causal effect of a predictor on the outcome. So yeah, that's what I would think as well. But we're going to talk about a situation where that approach may not necessarily work. So you guys see the slides? Okay. For some reason I don't see the green outline when that's kind of the telltale sign that things are working, but as long as you see it, that's good. So when we have, what we typically think is a predictor is the first thing collected, right? And then the outcome, there's probably a lag in time. It might be occurring on the same day or the next day, but you typically want the predictor as the cause, right? The X variable, and the outcome as the effect. And so you typically want to make sure that in time, the predictor comes before the outcome, right? So it makes sense that, that you would do that instead of, having the outcome and then later in time you have the predictor, that really wouldn't make sense, because you know that how can that X cause Y if it came later in time? So usually the predictor is going to be in time is the first thing, and then some amount of time lapses, and then it's going to affect Y. So a lot of times when we do modeling, we make sure that the X variable comes before Y in time. But when we have a situation where the outcome is actually going to predict a subsequent value of a predictor, and which can't be explained by previous X values, then we have a situation that's more complicated. And in addition, when there's a time varying confounder, we'll call it Z, that affects both X and Y, and the X history affects subsequent values of Z, we have a more complicated situation that we can't necessarily address by just including covariates in the model. And this is a situation, if we're interested in causal effects, where we want to try to apply something like marginal structural models. So real quickly, I'm just going to describe, a couple examples where this may apply, and then show you the methods. And I actually have a program I can show you as well. So as one example, consider the effect of cigarette smoke exposure on inhaler use. And I'm specifically thinking about the cohort that we have here at National Jewish, the kids that have asthma. And so they're a sensitive group, and obviously there's a concern if they're exposed to air pollution or cigarette smoke or things like that. So we want to know what is the impact that X has on Y, right? But the question is, what does how do asthma symptoms affect this relationship, this observed relationship that we have between X and Y? Okay, so as I mentioned here in the second bullet point, it's feasible that asthma symptoms not only increase the likelihood of inhaler use, but also affect subsequent exposures. For example, if a child with more symptoms is less likely to be in a smoke-filled environment, either based on their own decision, they don't feel well, so they're not going to be put in a situation where they're exposed to smoke, or the parent is aware, that the kid's not feeling well, so they make a stronger effort, if they smoke, to smoke outdoors or something like that. It's also feasible, if not likely, that cigarette smoke exposure history affects subsequent asthma symptoms. So we have this complicated relationship, and it becomes more complicated as we have this cyclical relationship occurring between the variables over time. And if our usual approach would just to be to put in cigarette smoke exposure as a predictor, inhaler use as the outcome, and then put in asthma symptoms as a covariate. But that doesn't necessarily take care of the this tangled web that we have, which we can better address with marginal structural models. So if we use the regression approach, this is what we're doing. We're looking at the expected value of Y, which is expected inhaler use. So again, so this is inhaler use, and X equals 1. I'm just simplifying exposure. Instead of actually using a continuous exposure, I'm just saying exposure to smoke. Given they have certain level of symptoms. And then on this side, this is the same thing. And then this X equals 0 would be no exposure to cigarette smoke. So if we take the regular regression approach, this is what we're estimating. And okay, it makes sense, but the problem is that when we do that conditional approach, the subjects can really choose their treatment based on their symptoms. What we really want is to randomize subjects, so we can consider this quantity. It's a marginal effect, expected value of Y1. That represents expected inhaler use for a subject randomly assigned to receive the exposure. And this would be the same thing. So Y1, the 1 indicates that they received the exposure. Okay, that's just the notation that we're using. And the expected value of Y1 is the expected inhaler use for somebody that's randomly selected and then randomly assigned to the exposure. And Y sub 0 is the same, but where they were not randomly assigned to receive the exposure. And so you can see the difficulty with this situation is that what we observe is only one of them, right? We only observe a kid on a given day that either that had exposure or not, and it wasn't randomly assigned. So this gets into the area of what we call counterfactuals, where we only observed one situation, but we really want to observe both. We want to observe a situation that we want to observe the inhaler use when they did receive the exposure, and then an alternative world where they didn't, okay? And we didn't observe that, but we want to observe those situations. We take the difference to see the actual effect that inhaler use had. Okay, so there's an analogous example I have in my mind where we think of climate change, right? And a lot of people are aware it's an important issue that we have to address, but then a lot of people are saying, well, how do we know it's really the increase in temperatures is due to human activity, right? So how could we actually answer this question? Well, if we had a world where everything was the same except there were no humans on it, right? And we could observe that, then we can compare our world where we have human activity and we've contributed to increases in greenhouse gases. Well, if there's another exact same replicate of the world where there wasn't any human activity, then we could see what the temperature was in the one world and then subtract it from the temperature from the other world at the same time. Obviously, we don't have the ability to do that, but that's what we would really want in order to estimate a causal effect of human activity on global temperature, right? So what we have in the situation is observational data, and what we're trying to do is apply methods as if we had a randomized experiment, okay? And we do that by applying the marginal structural model methods. Okay, so the way that we do that is we apply inverse probability of treatment weighting to reconstruct data as if subjects were randomized to treatments, and with the hopes of eliminating the confounding effects of symptoms with the particular application we're talking about here. And the longitudinal, this longitudinal component becomes very important here because we have a cyclical pattern of effects between these three variables that occurs over time. And so we're going to fit a longitudinal model, but the way that we address the confounding effects of symptoms, the time varying confounding effects, is to create weights, and we reweight subjects so that we can equalize the records to make it as if subjects were randomly assigned to exposures. Okay.
Hey Matt.
Yeah.
In the approach above, 2 slides above, where you have the expected values. Yeah. Can we think of it as matching these two different subjects or kids on other covariates, and then just checking where they were exposed and not exposed? Is it the same kind of approach or different? Well, we're assuming they're the same on other cases, except this situation where they were exposed and not exposed.
So what this really is theoretically, this is addressing when they were exposed and not exposed, like you just mentioned, right? But it's for the same exact kid, same time. So it's theoretical, right? And we can estimate that based on what you're talking about, if we can consider, the situations when they're exposed and not exposed. But the problem is that that may not address the randomization issue. Okay, so what we really want is for the same exact kid, same exact situation, controlling for everything. The only thing that we change is whether they were exposed to cigarette smoke or not. Okay, so we could do that by considering, the data that we have for exposure and non-exposure. But the problem really arises when we have this situation, okay? And this is why when these two conditions are occurring, we can't just use the standard conditional regression approach. Okay. So I don't know if that answered the question you had or not, Benjamin.
Yeah, to some extent. And then do we get to a point where we check if they are really the same on the other variables except this one? Do we check that, or we just assume once we control for them, they're the same?
I think we can. There's ways that we can check the assumptions for this marginal structural model. I think it's a little bit complicated because it's kind of like the missing data issue, right? When you do missing data methods, it requires assumptions, about what type of missingness pattern you have, right? And it's hard to check the assumptions because what you really need in order to check the assumption thoroughly is you need the data and you don't have the data. So with missing data methods, you have to make some assumptions that are difficult to check. And the way that you do it is you apply a lot of different missing data methods, and there's some information you possibly can get to see if the assumption makes sense, but you really can't test it thoroughly. And so I think in this case, it's a little bit similar to that, where you can try different modeling approaches, and there may be some things that you can test, but it's hard to verify it completely just by checking assumptions. You can't just do it by comparing to conditional assumptions. But what I'll do, I don't have the slides here, but I'll get a little more information to show how we would check the assumptions for marginal structural models. That's actually a good question that you have, Benjamin.
Can I ask a question, Matt?
Yeah.
So would you be able to permute your labels of treatment to create a null distribution, and then you can compare your observed to your null distribution to get that difference?
Describe that to me a little bit.
So you have your labels of exposure or non-exposure, and then you've got your children. If you permute your labels, you create a null distribution, and then you can compare that through your modeling with your observed distribution, and then you can get the differences between the two.
Okay. How would you incorporate the time factor into that, what you're
So
describing?
everything's still the same. You just permute the labels of the exposure, and then you fit your model, your longitudinal model. And then you can compare, because you have one model built on your observed distribution, and then one model, longitudinal model, built over your null distribution. And then the differences between the two are the differences between your permutation, your null and your observed.
Okay, using a permutation. Yeah, that's an interesting idea. I would have to think about that a little bit more. But you're saying the null distribution would be that there's no causal effect.
Correct.
Okay, and then how would you use that to, how would you use that to estimate the actual effect?
Well, if there's no causal effect, then you can go back to your observed distribution, right?
Yeah, but if there is, what if there is, and you're interested in estimating that causal effect, how would you do that? We can keep thinking about it. Yeah, that's an interesting idea. I'll give that some more thought, Jonathan. But I'm going to take a jump off here and open up a SAS program to show you how you would do the marginal structural model. So this is considering this is a situation where we're considering FEV1 as the outcome. Okay, so this is a lung function measure. So this is our main model right here. I'm gonna move this down. So our main model, you guys see the SAS program? Okay, so this is our main model where we have FEV1 as the outcome, and our main predictor of interest is doser use. So how does using the inhaler affect the lung function, right? And we would expect that when you use it, this is just a binary indicator, and the 1 at the end means that it's lagged 1 day. So how does doser use yesterday affect FEV1? We also have a 2-day lag in the variable. So how do doser use the previous day and 2 days ago affect lung function? Okay. Now the problem is the kids use the doser when they don't feel well, right? So if you actually were to regress, when you do this regression, the coefficient's actually going to be negative to make it appear like doser use is making FEV1 go down. But the reason why that is because the kids use it when they have symptoms, and when they're not feeling well, their FEV1 is going to be lower, right? So what we would normally do is we would put in asthma. This is a symptoms variable here. We would throw that in addition to everything else to try to untangle the confounding it has between doser use and lung function. Okay, so that you actually get an estimate that's that's improved when you do that. So this is not to say that this is a terrible analysis. It's much better than an analysis that doesn't have asthma symptoms in there. But I do call it a naive analysis because it doesn't allow us to get the best causal estimate of dose use on lung function. And the way that we do that with marginal structural models is to we do some initial logistic regressions where we regress doser use on a number of covariates. And then we do a second logistic regression, which is similar, but we add asthma symptoms, okay? And with these two logistic regressions, we can create weights, and I do that in this data step here, where we create a weight that is going to either upweight or downweight records based on whether it's more likely or less likely that they took that they had the doser in these situations or not. And then so we create a stabilized weight here based on these two initial logistic regressions, and we use that weight in the marginal structural model. So we're upweighting or downweighting records based on how likely they were to occur. So you're actually going to upweight records that were less likely to occur and downweight records that were more common in the data set. And so again, the goal is really to make it so that we're sort of mimicking a situation where they would have actually been randomized to one situation or the other. Okay, so in terms of the code that it requires to do this, it's not that complicated. We just have some initial logistic regressions. We create weights, and then we put that into the weight statement in our longitudinal model. So comparing the standard approach we take, or naive approach, versus the marginal structural model, you can see that it's not too outrageous. One thing that I have noticed is that when you have a weight statement, and this is true for the inverse weighting approach we talked about with missing data, they recommend that you actually don't use a correlation structure because it's going to affect the weights. So that's why typically I would remove the AR1 and I'd use variance components, which basically is going to allow us to estimate variances, but it won't have any covariance parameters in the model. And then to account for the fact that we're not using correlation structure, we'd use an empirical approach for standard errors, which should be more robust to misspecifications to the correlation structure. Okay, and in terms of our application, so this is one situation. The application we're talking about here is a similar one, but this is again considering the effect of smoke exposure on inhaler use using the marginal structural model approach. We're using medication is a binary, so we have logit link. So our estimate is in terms of odds. So we found that a recent smoke exposure increases odds of medication use roughly 3 times, and we have this confidence interval. This is using the marginal structural model. And if we just use a situation where we put in, we add in symptoms as a predictor, then the odds ratio is not quite as large. It's 2.5, and there's a confidence interval. If you do a regression without symptoms and you don't use marginal structural models, then it actually goes in the other direction. So you can see that by including symptoms in the model, that does help help get a closer estimate. But assuming that this is the right estimate here at the 3, then we're still a little bit lower if we use the standard regression approach. Any questions on that?
So is this similar to the idea of stratification, like mental Hansel? You adjusted your odds ratio based on each different situations, and then you combine all the things together.
Turn up the volume just a little bit. I guess you could think of it that way, but again, yeah, what the effect you're getting is what we consider a marginal effect. So it would be you don't end up with stratified effects. You end up with the marginal effect that you can't get by using standard regression. So I could say that maybe, yeah, it's similar, but it's a marginal effect averaged over, you know, the difference between whether they had smoke exposure or not in this case. Any other questions on that? I actually did I worked with a student, Vanessa Richardson. She worked on marginal structural models, and she just graduated. She gave her defense a couple weeks ago, and it was in the same area. And what she was looking at was how, you know, when we have this issue, this circular relationship that we're trying to untangle between symptoms, exposure, and an outcome, or whatever the predictor is in the outcome. Actually, what we have intermittent data. We don't have it on consecutive days, which adds another layer of complexity to the project. So she was studying how do you estimate these weights, you know, that you obtain from the first logistic regressions. How do you estimate those if we have intermittent data? So it was a pretty complicated project, but she did a really good job on it.
I have a quick question, Matt.
Yeah.
So if you're doing causal inference, how important is it that your confidence intervals are tight?
That's a good question. And I don't know if you, maybe Jonathan, you were looking at these confidence intervals here. And you do notice that we have larger confidence intervals. And I would say that's maybe one downside with the particular data set that we have here. We actually had shorter intervals here, right, for the standard approach. And we had wider intervals here. How important is it? I do notice it, and it is something that's like, wow, maybe we got a more accurate estimate, but we have more variability. It is a concern. It's a little bit of a concern, I think. It could be somewhat due to this particular data set that we have, which is not very large. And so that is a downside. I would say it's a downside of the approach that we have. But at the same time, if you have an estimate that's off, that's biased, what good is a really short confidence interval, right? It could be, especially if it's really tight, it might not even include the actual true parameter in that interval, right? So I guess that would be a counter argument to that. But that is a really good point that, you know, I'm aware of that yeah, the confidence interval is wider for this marginal structural model approach. And, you know, hopefully we can get more data in the future to get a more precise estimate. I was going to say something else here. Oh, the way that we did these estimates are based on taking the last weight and carrying it forward. If we didn't have data during the intermittent period where we didn't collect data, we just carried a weight forward. Whereas what Vanessa showed is that if you restart the weights when you get a new day, then we actually get better estimates. So in a nutshell, we refine this approach, which may actually help us get more precise estimates and hopefully better confidence intervals as well. So some of the methods are still being developed, with this to account for intermittent responses and things like that. So yeah, it's a fairly complicated methodological approach, and there's still some work to be done in this area. How do you, this is Benjamin, maybe going back to what you were talking about, how can we assess how good this method is? Simulation, I think, is one where you set up reality, right? And then you apply the methods and you can see how good it is. And that's one of the things that we did that I worked with Vanessa on. But actually simulating the data is not that simple in this case either, because we have this confusing relationship. And so you have to create a model where you're generating X, Y, and Z to have this complicated relationship. And we really struggled with that. It took a lot of time to even get results that made sense and where the marginal structural model could actually beat the naive approach. It sort of took, playing around with the model and the coefficients and things like that to get it to work. So, so I guess this isn't maybe a teaser, for Fan's course if you end up taking the causal inference course. I don't know how much she goes into this specific method, but she talks about causal methods, a variety of them in her course. So the next method that I'm going to talk about, and this is the last one, is measurement error models. And I'm going to kind of skim over these methods and why they're important and when you use them. But I think it's an area of research that's not utilized that much for a couple of reasons. I think one reason is because people may not understand the importance of it. And the other is because people may not have the data in order to be able to actually use it. So measurement error models, what are we talking about here? It's a set of methods that tell us how to account for measurement error in regression type models. And in particular, we're considering a situation where predictors in regression models have error. And I think that occurs probably more often than people realize. And, as we talk about this, people may be able to think, well, yeah, I have predictors that are measured with error. They're not exact values. And that would actually include predicted values of X. If you have data where your X variables are predicted and they're not actually observed values, that would fall into this area as well. So a couple examples. Let's say X is how many calories you consume during a day. And so, if you have a questionnaire that asks, what did you eat today? And you can estimate then the calories that you had. Well, obviously, if you're going to do it through a questionnaire, that's going to be an estimate, right? It might actually be lower or higher than what you said. You might conveniently forget some things that you ate, right? And so I would think that there might actually be a chance that it would be underestimated. Okay, you're probably not going to add some stuff on that you didn't eat. There's a chance it could be overestimated, but I would think that you might forget some things that you ate. And so if you use X based on a questionnaire, how many calories that you had on a given day, I would expect there would be error in that, you know, if you do this in a large study. So the question is, how do you account for that error? Another example is where, this is one we actually talked about. We're interested in kids that have exposure to pollutants and how that affects certain health outcomes that they have. And so we have ways of estimating exposure, but it's actually pretty difficult to get an accurate estimate of air pollution exposure on a given day for a given kid. And so we end up with estimates of it. One of the difficulties with respect to the research that I did was that we were interested in exposure specifically to outdoor sources and exposure due to like cigarette smoke. Now, if you take particulate matter and you have that measurement on a subject, even if you get the actual amount of particulate exposure, you have to estimate the sources, you know, how much of that was due to cigarette smoke, how much of it was due to outdoor sources. So even if you can get an accurate estimate of the actual exposure, partitioning it into different sources is difficult. So those are just a few motivating examples. Why is it important to worry about this? You know, if you have a measured with error version of X instead of an actual amount, and the reason is because it can attenuate the slope in regression. So X measured with error, if you just stick it in as a predictor, you're likely going to underestimate the slope when that happens. There's another type of regression in the situation where you can incorporate instrumental variables. And I'll talk about that more, I think, in a second. Yeah. So these are the two situations where you want to address measurement error. One situation is where we use regression calibration, and you can, you know, the attenuation that's observed when you use X measured with error. If you have residual variance in the model, and you have an estimate of the variance of the error of the mismeasured predictor, then you can adjust that slope. You can account for that attenuation. Now, this is the hard part, though, is actually getting this. Okay, getting an understanding of the error that you have in X. And that's why I think probably these methods aren't used more than they should be, is because it's hard to estimate that. You need to get that information. But if you have this other situation where you actually have an instrumental variable, and that is essentially a variable that's linearly related to that predictor that's measured with error. It could be anything as long as it's linearly related to it. If you have that, then you have some instrumental variable plus a mismeasured predictor. Then what you can do is you can regress the mismeasured predictor on the instrumental variable to obtain predicted values of the unobserved variable, and then you substitute those in for the predicted values of for X. And then you can get an unbiased estimate of the predictor of X that you're really interested in. So these are some of the things I've already mentioned. So I'm sure. Oh, that one's there. So I'm going to show you, you know, I could show you some of the math behind it, but I think it may be more intuitive just to show you simulated data. So let's say we have, going back to the calorie intake, where we have W is an estimate of that based on maybe a survey or something like that. So what we get for calorie intake is W, which is, let's assume that that is related to the actual calorie intake X in this relationship, where U is the error in the difference between X and W. Okay, I would think that in real life, that may actually be a tendency for W to be less than it should be, so it would be biased low. But let's just say that it's unbiased, that we can make some adjustment for, you know, underreporting, and that W is equal to X plus U. So X is the actual calorie intake, U is some random error that has mean 0. So the question is, if we regress Y, well, let's say that's BMI, and we want to understand the relationship between BMI and calorie intake, and you'd assume that there would be some relationship there. Let's say it's a linear relationship. What can we expect if we plug in W instead of X? What's going to happen to the slope? And then let's say in another situation, instead of adjusting or changing X, that we change Y. So let's say that we have calorie intake is as the outcome, and our predictor in that case is mood level. So we're using a new version of the outcome rather than Y. So we have two situations, one where X has error in it, and one where Y has error in it. What's going to happen for the regressions in those two cases? Well, when X is measured with error, this is what's going to happen. We have the actual relationship is given in the solid black line, and the relationship when we regress, so this is regressing Y on X, and this is regressing Y on W. So what happens? You can see that there's an attenuation like I talked about. If we use a measure with error version of X, we see the attenuation. In other words, a flattening of the slope of the line. But look at what happens if Y is measured with error. What happens? Not much. And in fact, the expected value is going to be the same. So this shows you that if Y is measured with error, what's going to happen is that error is actually going to get absorbed into the general error term in the regression model. So if Y is measured with error, that does not cause an expected bias in the slope of the regression line. Whereas if X is measured with error, it does cause bias in the slope. So this is simulated data, but you can show mathematically that it's going to hold up as well. So the last thing I can talk about is just an application of regression calibration with instrumental variables. So this is a situation where we have, we're going to apply regression calibration to, so that we don't get the attenuation in the slope. And we also have instrumental variables that we're going to use in this process. Okay, and I actually talked about this. I talked about this maybe 2 or 3 weeks ago, where this is a project that I worked on where we're considering the exposure that kids had to cigarette smoke, and and then also ambient air pollution. So X1 is the exposure to cigarette smoke, and X2 is exposure to air pollution from outdoor sources. So it could be automobile exhaust or industries that are emitting pollution. And so that's what we're really interested in these actual exposures. But what we get, we can only estimate those. So those are W1 and W2. We have estimated amounts of those. And we also have instrumental variables. One is cotinine, and that's actually a biomarker that's measured. We get that from urine samples, and that's a marker of cigarette smoke exposure. It's in different units, but it's linearly related to the actual cigarette smoke exposure. And then we use a fixed outdoor monitor for the other instrumental variable. So M1 is going to be an instrumental variable for cigarette smoke exposure. M2 is going to be an instrumental variable for exposure to outdoor air pollution. So what we do is we're going to actually regress W1 on M1, so the measured with air version of cigarette smoke exposure on cotinine, and then we regress the measured with air ambient exposure on the data from the fixed monitor. And so we get predicted exposures to cigarette smoke and outdoor air pollution, and we substitute those in for the unobserved X1 and X2 in the health outcome models to get our estimates. And what we come up with, and this is what I described a little bit before, we saw that the steepest dose response relationship between a pollutant and health outcome occurred when the second pollutant was lower, which occurred because there was a significant negative interaction between the pollutants. Okay, we also saw that cigarette smoke was actually more toxic than ambient air pollution, at least in this area, where the kids did the study here. And this, if you're interested, I can forward you a paper that we just had published on this. But this was a complicated situation because we not only had one predictor measured with air, we actually had two, and there was interaction between them. So it was kind of a complicated model, but we were able to understand what's happening between these two types of air pollution exposures and the health of kids with asthma. Okay, so the last slide, I think this is it. This issue of mismeasurement, like I said at the beginning, if you have a situation where you have data where your X variable is based on a predicted value, you also have unobserved data. You have estimated values that you're plugging in, and really you need to account for that uncertainty in the model. So if you have predicted X values in regression, you can probably expect the standard errors to be underestimated unless you account for that variability in some way. And it's possible to use the regression calibration with instrumental variables in order to account for that extra variability and adjust the standard errors accordingly. You probably need to inflate your standard errors a little bit to account for that. So that's just one comment. I think it's pretty common, for data to have, predictors that are based on predicted values rather than observed values. So this is just something, for people to be aware of, I think. And if you have any questions on that, be happy to talk about it in more detail with you. So we talked about two fairly complicated things today: the causal modeling and measurement error models that I've done some work in, and maybe hopefully that just gives you a sense of how they work, and maybe if you come across these issues in your data in the future, I'd be happy to talk more with you if you have any questions on it. Any questions that you guys have on either one of these? I will, the couple of good questions that came up, I'll see if I can get some more information on those. So what we have left are, 3 days of presentations from you guys. And then we have a review day, the last day. Any thoughts about what you want to talk about in the review, or any questions about, getting ready for the last quiz, or more generally things that, questions that you have that you want to discuss more? No? Let me know if you do. Just send me an email. Otherwise, I'm going to talk to Emily today and Benjamin, right? And then Samantha, were we going to talk today or another day? Are you still there?
Today.
Today. Did we set a time yet, or did we just say after class?
I think, yeah, we just said after class.
Okay, so for those of you, so Emily, Benjamin, Samantha, we can talk. If you guys want to stay on, we can figure out, the order for that. And anything else we needed to discuss? Let me